Assalamu alaikum. Myself Shafaq Nawaz, and today the topic of my presentation is role of metals in body, presented to Dr. Hammad Majeed. First of all, the table of contents which are related to our presentation topic, which are listed below. First of all, introduction of metals, then essential metals, toxicity of essential metals, non-essential metals, toxicity of non-essential metals. At the sixth number, coordination chemistry, Werner theory, applications of coordination compounds, complexes of sodium and potassium, metal with their geometries, table, and at the last, references. So, first of all, the brief introduction of role of metals in our body. Metals are a part of our daily life. They are used for construction and for countless products. For example, cars, mobile phones, or computer. Without the use of metals, human society would have not been developed to its current stage. While the raw materials are provided by our planet, humans learn to extract metal from mineral ore and to refine them. As a consequence to their wide use in the modern world, we are all exposed to metals and metal compounds to a degree that was rare before the industrial age. Some metals serve critical functions in a human body. Iron is a necessary component of hemoglobin in red blood cells. Copper, manganese, zinc, cobalt, chromium, molybdenum, and selenium are all required as enzyme cofactors or prosthetic groups. And human disease results if the diet is deficient in the metals. However, exposure of humans to a successive levels of physiological metals are associated with the disease. Other metals, for example, lead, aluminium, and arsenic, have no known beneficial effects in our human body and have only toxin actions. The figure, which is mentioned in a slide, elements in a human body and the concentration of elements in a human body. 96% elements are the bulk elements, major elements which are present in body 3.5%, and trace elements only 0.5% are present in our body. Essential and non-essential metals. The essential metal ions for humans are the bulk metals, sodium, potassium, calcium, and magnesium, and the trace metals, magnesium, iron, cobalt, copper, zinc, and molybdenum, since they play an important role in a biological system. Whereas non-essential metals such as chromium, nickel, lead, and cadmium are toxic even in the trace amounts. The essential metals can also produce toxic effects at higher concentration. The toxicity of non-essential metal ions is a consequence of environmental exposure leading to the accumulation within the body where they interfere with the functions of essential metal ions. Both types of metal toxicity can in principle be treated by the use of appropriate metal insulators. The figure, which is presented in a slide, essential metals and non-essential metals and their concentration at their moderate, accurate, high, and excessive rates, which are present in a graphical form. Essential metals. There are around 25 elements that are required by the biological system, including an important number of metal ions. However, for humans, there are 10 essential metal ions. Out of these, 4 sodium, potassium, calcium, and magnesium can be considered as bulk element and together constitute approximately 99% of metal ion content of a human body. The other 5 transition metal, manganese, iron, cobalt, copper, zinc, and molybdenum, are known as trace elements with much lower dietary requirements than the bulk elements. They are nonetheless indispensable for the human life. The concentration of element in a diet and in which are presented in a graphical form and divided into a maximum 5 parts: death, deficient, optimum, toxic, and death rate. The first essential metal is potassium and a sodium. Sodium and potassium, the two essential alkali metal ions, sodium and potassium together with hydrogen and chlorine, are only weakly bound to organic ligands and are extremely mobile. This makes them ideally suited to generate ionic gradients across biological membranes and to exposure the maintenance of osmotic balance, and this is precisely what they do. The sodium and potassium contents of the average 70 kg adult human are about 100 gram and 140 gram respectively, but their distribution in most mammalian cells is quite different. Sodium together with chlorine is a major electrolyte in the extracellular fluids, whereas potassium is retained within the cells. The concentration of a sodium in the extracellular fluid, like plasma, is maintained within the narrow limits at about 144 millimole per liter, whereas the intracellular concentration is about 12 millimole per liter. In contrast, the concentration of a potassium is 150 millimole per liter within the cells and typically 4 to 5 millimole per liter in the extracellular fluids. This concentration differential, which is maintained by the ATPase of the plasma membrane, ensures a number of major biological processes such as cellular osmotic balance, signal transduction, and neurotransmission. The second most important essential metals, which are magnesium and calcium. In contrast to sodium and potassium, the alkaline earth metals, potassium and calcium, have intermediate binding strength to the organic ligands and are therefore less mobile. They play important structural and catalytic roles, and in the particular case of calcium, serve as a charge carrier and trigger for signal transmission within the cell. Calcium is the fifth most abundant element and most abundant metal ion in the human body, representing 14% of body mass. Most 99% of our body calcium is found within the biominerals that constitute bone and teeth, but the 1% found within the cells and tissue has enormous importance in regulating a series of important cellular response, from initial fertilization to being a harbinger of cell death. Inventing between these limits of life of a cell to include secretion, mobility, metabolic control, cymatic regulation, and gene regulation. Although magnesium represents the least abundant of the bulk metal, it is the most abundant cation within the cells, with roughly half of the cytosolic magnesium bound to ATP and most of the rest bound together with the potassium to ribosomes. The intracellular concentration of a free magnesium to around 0.5 millimole and less than 0.5% of a total body magnesium in the plasma. Unlike the other three bulk cations, magnesium has a much slower water exchange rate, allowing it to play a structural role, for example, participating in the ATP binding in many enzymes involved in the phosphoryl transfer reactions. 6 of the 10 reactions of glycolysis are phosphoryl transferase. The third most important essential metal is zinc. Zinc is a nutrient that plays many vital roles in your body because your body doesn't naturally produce zinc. You must obtain it through food or supplements. Zinc is required for numerous processes in your body, including gene expression, enzymatic reactions, immune function, protein synthesis, DNA synthesis, wound healing, and growth and development. Zinc helps keep your immune system strong because it is necessary for immune cell function, and cell signaling. A deficiency can lead to a weakened immune response. Zinc supplements stimulate particular immune cell and reduce oxidative stress. For example, a review of 7 studies demonstrate that the 80 to 90 milligram per day of zinc may reduce the length of the common cold by up to 33%. What's more, zinc supplements significantly reduce the risk of infections and promote immune response in older adults. Deficiency symptoms. Although severe zinc deficiency is rare, it can occur in people with rare genetic mutations, breastfeeding infants whose mother don't have enough zinc, people with alcohol addictions, and anyone taking certain immune suppressing medications. Symptoms of severe zinc deficiency include impaired growth and development, delayed sexual maturity, skin rashes, chronic diarrhea, impaired wound healing, and behavioral issues. Zinc deficiency impair your immune system, increasing the chances of infection. Zinc deficiency is thought to cause over 450,000 deaths in children under 5 every year. Zinc deficiency is difficult to detect using laboratory tests due to your body tight control over zinc levels. Symptoms of a mild zinc deficiency include diarrhea, decreased immunity, thinning hairs, decreased appetite, mood disturbance, dry skin, fertility issues, and impaired wound healing. Other essential metals. The other 5 transition metal ions, manganese, iron, cobalt, copper, molybdenum, bind tightly to the organic ligands, are therefore effectively immobile and participate in a wide range of redox reactions. Iron also plays an important role in the oxygen transport and storage proteins, hemoglobin and myoglobin, while both iron and copper are involved in oxygen activation and detoxification. Cobalt is required in the diet as a vitamin B12 and is an essential cofactor for a number of B12-dependent isomerases and methyltransferases. Manganese plays an important role in the detoxification of oxygen-free radicals. Molybdenum, while relatively rare in the Earth's crust, is the most abundant transition metal in seawater and is an important component of nitrogenous, the key enzyme of nitrogen-fixing organisms. However, in human, there are a number of molybdenum-dependent enzymes which all contain molybdenum in the form of molybdenum pyropyridine diethylate cofactor. They include xanthine oxidase involved in the catabolism of purine bases, sulfide oxidase involved in sulfur metabolism, and aldehyde oxidase involved in the metabolism of many drugs. Toxicity due to the essential metals. Everything is poisonous and nothing is not poisonous. Only the dose determine whether something is poisonous or not. Nowhere is this more true than in describing the toxicity of essential metal ions. The concentration of each of metal ion need to be maintained within strict limit in each cells and tissue of a body. Nutritional deficiencies of essential metals can increase the hazard from lead exposure by enhancing absorption and toxicity of dietary lead. The essential metals with the most marked influence on a blood level and toxic effect are dietary levels of calcium, iron, and zinc. First of all, potassium, sodium, and high blood pressure. Increasing your potassium intake can decrease your blood pressure if you have high blood pressure. Consuming too much sodium can raise your blood pressure. This means that on average, the more sodium you consume, the higher your blood pressure will be, especially if you already have high blood pressure, also known as hypertension. Consuming too little potassium in your diet and too much sodium can raise your blood pressure. Potassium, sodium, and the risk of heart disease and stroke. Increasing potassium intake can reduce your risk of heart disease and stroke by lowering blood pressure. Consuming too little potassium and too much sodium can increase your risk of heart disease and stroke. Lowering blood pressure reduces your risk of heart disease and stroke. Toxicity due to the calcium. Hypercalcemia or higher than normal level of calcium in your blood is a fairly common finding. Blood tests such as those drawn for an annual physical exam today routinely check calcium levels. This allows physicians to detect abnormally high calcium level early. In the past, complications such as bone loss and fractures, kidney stones, kidney failures, hypertension, and were commonly found as a result of a long-standing untreated high calcium levels. These are now rarely seen thanks to blood tests that led to preventive treatment. How is hypercalcemia diagnosed? Your doctor will order a blood test to determine if you have hypercalcemia. If the calcium is elevated, your physicians will often review your medications and medical history as well as conduct a physical exam. If there is no obvious cause, your physician may ask you to see an endocrinologist who will give you further evaluations and testing. Calcium level that is too high is also harmful to the blood. Abnormally high blood calcium levels are usually due to the certain disease condition rather than excessive calcium intake. With excessive intake, the intestines are programmed to shut off further absorptions, which prevent calcium intoxications. The causes of high blood calcium level include bone cancer, overreactive thyroid gland or hyperthyroidism, overactive parathyroid gland or hyperparathyroidism. Toxicity due to the zinc. The human body contains about 2 grams of zinc, mostly found in a test muscle, liver, and brain. Zinc deficiency due, for example, to poor nutrition, aging, and end of zinc homeostasis is much more frequently encountered in the all human population than zinc excess. The most common cause of a zinc excess is taking too many zinc supplements. Other causes are less common if your kidneys are not working well. Acute kidney injury does not mean you have had a physical trauma to your kidney. It is a sudden loss of kidney function, usually due to an illness such as severe infections. If you have an uncommon condition called hemochromatosis, you are more likely to get zinc overload. Certain industrial compounds have high level of zinc, and it is occasionally possible to get zinc poisoning through exposure to these substances. These include some pesticides and some components used as paints, dyes, and rubber. Symptoms of zinc deficiency and zinc excess. Deficiency symptoms include not wanting to eat, lose weight, lose stools, having no energy, being more prone to infections such as cold, cough, and chest infection, losing your hairs, skin rashes, problem with eyesight, taste, or smell, and impotence. Excess symptoms which are related to the zinc deficiency. A number of a different symptoms can occur if you have too much zinc in your system. For example, tummy, abdominal pains, diarrhea, feeling sick, being sick, headache, tiredness, and dizziness. Other essential metals. Toxicity of a cobalt. Cobalt is an essential micronutrient in the form of a vitamin B12, present as a corin cofactor in several enzymes, but inorganic cobalt is not required as such in human diet. Cobalt is acutely toxic in large doses, and consequences were dramatically observed in 1960s among heavy beer drinkers when cobalt salts were added to beer as form stabilizers, resulting in severe and often lethal cardiomyopathy. Manganese toxicity. Overexposure to manganese led to toxicity, particularly neurotoxicity. Neurons are much more susceptible than other cells to manganese-induced toxicity, and accumulation of manganese in the brain result in the condition known as manganism, first observed in minor during the 19th century. Current treatment strategies combine chelation therapy and iron supplementation, the latter to reduce manganese binding to proteins that interact with both manganese and iron. Iron and copper toxicity. Both iron and copper are characterized by genetic disorders associated with the accumulation of a metal in particular tissues, resulting in toxic consequences. Too much copper can be fatal. You could get severe toxicity from ingesting large amount of copper salt through your skin. Copper can work its way through your internal organ and build up in your brain, liver, and lungs. People who have copper toxicity can become very unwell. Iron toxicity can be classified as corrosive or cellular. Ingested iron can have extremely corrosive effect on the gastrointestinal mucosa, which can manifest as the nausea, vomiting, abdominal pain, hematemesis, and diarrhea. Patient may become hypovolemic because of significant flood and blood loss. The therapeutic dose for an iron deficiency is 3 to 6 milligram or otherwise kilogram per day. Toxic effects begin to occur at the doses over 20 milligram or kilogram of the elemental iron. Ingestion of more than 60 milligram to kilogram of elemental iron are associated with severe toxicity. Molybdenum toxicity. The last of the essential transition metal ions, molybdenum, is present within the deuterium-based molybdenum cofactor MoCo in the active site of a mammalian enzymes. And while there is a large literature concerning the frequently fatal consequences of molybdenum deficiency, causes of molybdenum toxicity are much rare. A recent study established the long-term carcinogenic potential of a molybdenum, the main inorganic chemical constituent of MTM particulate matter. Now, the further topic is toxicity due to the non-essential metals. The toxicity of heavy metal is one of the oldest environmental problem and remain a serious health concern today. Alternatively, heavy metals used to defined as dense particle metals or metalloids which were potentially toxic, notable in an environment context. Typically, heavy metals are cadmium, lead, mercury, and arsenic. We prefer to designate the heavy metal as non-essential toxic metals, and we will devote the most of our attention to cadmium, lead, mercury, and arsenic. Lead. 30 years ago, Jerome Nerogia argued in a paper which was widely discussed in the press at the time that Roman civilization collapsed as a result of chronic lead poisoning. Lead toxicity affects several organ systems, including the nervous, hemotaptic, renal, endocrine, and skeletal systems. Despite numerous global initiatives to reduce the use of lead exposure remains a widespread problem, particularly in the developing world. Lead appear to target proteins that naturally bind calcium and zinc. Example of proteins that are targeted by lead include synaptocatics, calcium sensor in the neurotransmission, and amino avalylate synthesis, enzyme in the heme biosynthetic pathway. Despite in size, lead can substitute for calcium in a synaptocatics and zinc in alert. Human ALAD is activated by zinc with a km of 1.6 pm particulate matter and inhibited by the lead with a concentration of 0.07 pm. Lead and zinc appear to compete for a single metal binding site. Cadmium. Cadmium, a soft Lewis acid with a preference for easily oxidized soft ligands, particularly sulfur, can displace zinc from proteins where the zinc coordination environment is sulfur dominated. While an account of similarity of its ionic radius with that of calcium, it can exchange with calcium in calcium binding proteins. Cadmium bioavailability and retention is favored by the poor iron status. Cadmium occur in the environment naturally and as a pollutant emanating from industrial and agriculture sources. At the cellular level, cadmium affects proliferation, differentiation, and causes apoptosis. The most commonly used therapeutic strategy for heavy metal poisoning is chelation therapy and to promote metal excretion. Chelators and meso-2,3 dimer acid have been reported to have protective effect against cadmium toxicity. Next, mercury. The brutal reality of a mercury toxicity was highlighted in 1956 by an environmental disaster that struck the population of Minamata, Japan, and its surroundings. We now refer to mercury toxicity as Minamata disease. The three biological forms of a mercury, organic mercury, metallic mercury, and inorganic mercury compounds, principally mercuric chloride. Mercury was the one responsible for the Minamata hecatomb. The brain is the principal target tissue of a mercury and its major toxic effects on the central nervous system, accumulating particularly in astrocytes. In reality, while selenium can act as an effective blocker of mercury toxicity, the biological effects of mercury are much more direct. Aluminium. Aluminium, although the most abundant metal in the earth crust, has been excluded from biological system essentially due to its lack of bioavailability. The toxicity of aluminium is associated with anemia, osteomalacia, hepatic disorder, and certain neurological disorders, notably Alzheimer's disease. The molecular target of aluminium toxicity involves disruption of the hemostasis of essential metal ions, notably iron, calcium, and magnesium. Aluminium can replace calcium in the bone and interfere with the calcium-based signaling events, while magnesium binding to phosphate groups on cell membrane, ATP and DNA can be replaced by aluminium. However, it is likely that the main target of aluminium toxicity are iron-dependent biological processes. In the cytosol, aluminium is unlikely to be incorporated into ferritin, which requires redox cycling between iron 2 positive and iron 3 positive. It seems likely that most aluminium accumulates in a mitochondria where it can interfere with the calcium hemostasis. So the next topic, which is related to the metal and non-essential elements, essential and non-essential metals, that is coordination chemistry of our metals. Coordination chemistry is the study of a compounds that have a central atom, often metallic, surrounded by molecules or anions known as ligands. The ligands are attached to the central atom by dative bonds, also known as coordinated bonds, in which both electrons in a bond are supplied by the same atom on the ligand. Coordination compounds are compounds in which a central metal atom or ion is linked with a number of ions or neutral molecules by coordination bonds or which contain complex ions. The picture which is represented in slides, the toxic metals and the organ toxicity disrupt the macromolecule mechanism of action and with their references. And the toxic metals which are involved in mercury, lead, chromium, cadmium, and arsenic, which damage organs. Properties of coordination compounds. The coordination compounds formed by the transition elements are colored due to the presence of unpaired electrons that absorb light in their electronic transitions. For example, the complexes contain iron 2 can exhibit green and pale green colors, but the coordination compounds containing iron 3 have a brown or yellowish brown color. When the coordination center is a metal, the corresponding coordination complexes have a magnetic nature due to its presence of unpaired electrons. Coordination compounds exhibit a variety of a chemical reactivity. They can be a part of inner sphere electron transfer reaction as well as outer sphere electron transfers. Complex compounds with certain ligands have the ability to aid in the transformation of molecules in the catalytic or a stereometric manner. Double salts and coordination complexes. Double salts are completely ionizable in aqueous solution, and each ion in a solution gives the corresponding confirmatory test. Example, potassium is a double sulfate. It is on ionization, it gives potassium sulfate and aluminium ions which respond to the corresponding test. Coordination complex. Coordinate complex are uncompletely ionizable in the aqueous solution. These give a complexation which does not show complete ionization. Potassium ferrocyanide, it ionizes to potassium and ferric cyanide ions. Types of coordination complexes. Cationic complexes, anionic complexes, neutral complexes. Hemoleptic complexes, heteroleptic complexes, mononuclear complexes, and polynuclear complexes, which have further their definition and examples. Cationic complexes in this coordination sphere is a cation. Anionic complexes in this coordination sphere is anion. Hemoleptic complex, the complex consists of similar type of ligands. Heteroleptic complex, this consists of different types of ligands. Mononuclear complexes in this coordination sphere has single transition metal ion, and polynuclear, more than one transition metal ion is present. This is the example of a polynuclear complex. Next one is Werner theory. Alfred Werner in 1898 proposed Werner theory explaining the structure of a coordination compound. Werner experiment by mixing silver nitrate with all the cobalt calcium nitrate, all three chloride ions got converted to silver chloride. However, when silver nitrate was mixed with cobalt chloride and nitrate, 2 moles of silver chloride were formed. Further on mixing, 1 mole of silver chloride was formed. Based on the observation, the following Werner theory was postulated. Postulates of Werner theory. The central metal atom in the coordination compound exhibit 2 types of valency, namely primary and secondary linkages or valencies. Primary linkages are ionizable and are satisfied by the negative ions. Secondary linkages are non-ionizable. These are satisfied by the negative ions. Also, the secondary valency is fixed for any metal and is equal to its coordination number. The ions bounded by the secondary linkages to the metal exhibit characteristic special arrangement corresponding to the different coordination numbers. This is the difference between the secondary valency and primary valency. Primary valency, they are ionizable, satisfied by the charged ions. Primary valency does not help in the structure of complex, and it can also function as a secondary valency. Secondary valency, they are non-ionizable, satisfied by the ligands. Secondary valency help in the structure. It cannot work as a secondary valency. This is the example of a Werner complex. Limitations of Werner theory. It fails to explain the magnetic, color, and optical properties shown by the coordination compounds. It failed to explain the reason why all the elements don't form coordination compounds. It failed to explain the directional properties of bonds in the coordination compounds. This theory does not explain the stability of a complex. This theory could not explain the nature of complexes. Applications of coordination compounds. The color of the coordination compound containing transition metal causes them to extensively used in the industries for the coloration of metals. They find application in the dye and pigment industries. Some complex compounds containing cyanide ion as a ligand are used in the process of electroplating. These compounds are also very helpful in photography. Coordination complexes are very useful in the extraction of many metals from their ores. For example, nickel and cobalt can be extracted from their ores by a hydrometallurgical process involving ions of coordination compounds. Hemoglobin consists of heme complex ion, which has tetrapyrrole poryphosphine string structure with a central iron ion. Vitamin B12 consists of a tetrapyrrole porphyrin ring complex with the central cobalt ion, and its coordination number is 6. Nickel is estimated using a complexating agent dimethylglyoxime DMG. The hardness of a water is estimated using complex of a calcium magnesium with EDTA. In medicine, cisplatin is used in a treatment of cancer. In photography, developing of the film involves complex formation. In metallurgy, in the extraction of gold, silver by MacArthur Forest process involved in a complex of cyanide ions. Complexes of a potassium and geometry of a potassium. Potassium is a cation and a complex ion in the anion. Since there are 4 potassium binding with a complex ion, the charge on the complex ion must be -4. Since each ligand carries -1 charge, the oxidation number of iron must be +2. The common name of this compound is potassium ferrocyanide, and the structure of a potassium hexocyanophyrate in chemical structure. Complex of sodium. Although less common than transition metal complexes, sodium does form complexes with some ligands, particularly oxygen-based ligands. Aqueous complexes are formed in aqueous solutions. Sodium forms many complexes with crown, ethers, cryptopents, and other related ligands. For example, 15 crown 5, NaOH 15 crown 5. Other metal ions and their geometry. Other metal ions which are involved: magnesium, manganese, cobalt, manganese, zinc, cadmium, and calcium. Ionic radius of magnesium 0.86, manganese 0.81, cobalt 0.89, manganese to positive 0.83, zinc to positive 0.88, cadmium 0.95, and calcium 1.1. And coordination geometry, the magnesium have octahedral, tetrahedral, or square planar geometries. pK of water molecules of different metal ion which are mentioned in a table. TD represent in the geometry tetrahedral, SQ represents square planar, TBP represent trigonal bipyramidal, octahedral, OCT represent octahedral, PBP represent pentagonal bipyramidal, and HBP represent hexagonal bipyramidal geometry. Even though zinc can form octahedral complexes, the majority of zinc complexes are tetrahedral. And the references of the presentation topic which is mentioned in a slide. And this is my whole presentation topic. Thank you so much.